small based on the scaling. So I've just kind of expanded it out a little bit. Let's look at the, let's do a line for males and a line for females, or a curve for males and a curve for females, I should say. So here's some illustrative points, and you can put this equation into Excel and just say, make a column of 1 to 40 for every hour, and then just plug, right in the equation and reference back the number of hours and drag and drop and make all the numbers just to graph this in Excel. But if we plug in the numbers, here's the so here's our equation for males. So this would be 0, and this times 0 hours. Oh, well, think about that. If I'm male, just a quick little review. If I'm male, female is equal to 0. We didn't center work, so work is 0 and work is 0 times 0. So if I'm male and work 0 hours, my predicted score is 3.52, which is the intercept, which is 3.526, which rounds to 3.53. So I didn't do a mistake, at least not an obvious one. And then female, it's going to be zeros for that, so it's going to be 3.53 plus 3.34-ish, but that's not going to quite make it, so it's going to be 3.3-ish. So 3, yeah. I'm just talking to myself, but the math works. Then we plug in 10 hours times 10 hours, 20 hours times 20 times 2,400, 30 here, 30 times 3,900, 40 times this minus 40 times 40, 1,600. And you get these numbers, these values. If we graph it, here's what we see. Females, females have higher GPAs, and it kind of goes down as the hours work more. Males have slightly lower GPAs, but they also kind of crash as work goes up, kind of like what we thought. It's clearly curvilinear in that it's fairly flat up here. That's sort of a plateau effect. You can work 10 hours a week, and it's not really hurting your GPA. But boy, once you're up at 20, 30, 40 hours, predicted GPAs are going down more. It's harder to keep the GPA up if you're working full time. Now, a couple things with this. Notice they're not lines. And I don't know if you can even technically use the term parallel, but they're parallel curves. It's exactly the same distance at every point. Females are always exactly, what was it? They're always exactly 3.38071 higher than males, everywhere down the curve. That's because, there's no interaction between gender and sex. Between gender and hours worked. So just like we saw when there was no interaction with the lines, you had two parallel lines. You can have a curvilinear effect, but if there's no interaction, the curve is exactly the same for the various groups. No difference. Just one's higher than the other, but the shape of the curve, the average distance between the curves, the difference in GPA is always exactly the same. Your girls are 3.8 higher here. I should say women are, because these are college students, right? Women are, they're working. Women are 3.8 points higher there. It's always exactly the same. And that's just a constraint of the model. We tell the software what statistical model we want, or we think, and it'll give us the best solution. But it may not be the right one. It may not be that the curve is exactly the same. But the model we said is this model. And that's what it'll give us. It'll give you back what you ask it to. In that sense, there is some truth to the, garbage in, garbage out. If you put in a garbage model, it'll give you the best fitting model, but it'll still be garbage. So something to always keep in mind as we kind of, along this line is different. As your model the you can design your model with different degrees of complexity to capture different sorts of patterns in the data, from very simple to fairly more elaborate. So for example, let's just to illustrate, let's say that I've got a regression model that has no predictors and only an intercept term. A really, really boring model. This is what it would look like. And let's say I'm predicting GPA. This is the result. This is my regression equation, whatever beta 0 is, or it's the average. This model will only give me the average GPA. That's all it'll give me. On the other hand, if I have, this is a model where now I'm predicting based on the intercept plus gender, this is what it's going to give me. 2 points, that's it. The average for this group and the average for that group. That's what that regression model will generate. If you do I was going to say if you do an ANOVA, that's actually kind of the equivalent to a t-test. This, let's say we have categorical variables, 3 groups, and the same thing, African American, Hispanic, and maybe white is the referent group. You've got 3 points, 3 averages, 1 for each group. That's what that regression model is going to generate. It can't look any different than that. That's an ANOVA. Let's say that, kind of just to illustrate, let's say that I want to look at hours spent studying and there's no effect. Let's say that there's no effect for that. So I have my intercept plus some regression coefficient times a non-significant continuous variable. This is what the model would look like. It's going to be flat, right based at the average number or the average GPA. And if this is truly 0, your regression model is going to be a perfectly flat line right at the average of whatever your outcome is. Hopefully that's not true. If you've got 2 variables, a dichotomous variable and a continuous variable that's not significant, this is what the model is going to look like. So this may be females have a higher GPA than males, but studying has no effect. So it's 2 flat parallel lines. Now, what if you've got it the other way around? The continuous variable is significant, but the categorical variable is not. This is like we were talking about a little bit earlier, that are they parallel lines or just one line? This is exactly that. What if there is no gender difference? Then it's just one line, and notice it goes red, blue, because it's both males and females from the previous example, but just superimposed on each other. It's just one line for both groups. And that's what happens if your regression model looks like this. This is the sort of thing it's illustrating. Now, what if both are in fact significant? So if I run a regression analysis and this is my regression model, and this is the regression equation I use, this is what I'm testing. Whatever the data actually looks like, my results will look something like this. It'll get as close as it can to reality, but it's going to have to look like this. 2 straight parallel lines. No matter what else is going on, if that's the model I've entered. By entering the interaction, now I can have a model that looks like that. Okay, they're still straight lines, but they're no longer parallel. So the interaction, that's the difference that we get by adding the interaction. Again, the other model, it doesn't matter. This might be how the data looks. The data could look like, but if I don't put in the interaction, it's going to give me 2 straight lines. Now the upside, let's say I put in the interaction, but it really is 2 straight lines. the regression equation will just come back and say, oh, that's 0. And it'll give you a model that's 2 straight lines. So putting the interaction in when it's not significant won't lead you astray. But not having the interaction when there is one will screw you up. Something to keep in mind. So if you think there's an interaction, it's better to test it than just stick your head in the sand and hope that you don't want to have to do that extra writing. We're almost done. The curvilinear, we just talked about that, right? A curvilinear where we have then a categorical variable. That's kind of exactly what we just saw, right? Two parallel curved lines. Now, you can have, you might start to think, well, can I do an interaction, right? We got past the parallel straight lines with an interaction. You can actually have an interaction. This is what's called a linear interaction with the curvilinear terms. Hours is how many hours you study the curvilinear effect. But you can then do a gender times hours interaction. And notice what happens, that the curve is the same shape, but one is now, the optimal levels change. Oh, here, this number of hours is optimal for that group. That number of hours is optimal for that group. The curve is still the same shape. So if the curve, it's exactly the same curve, but it's just shifted to the left or shifted to the right for one of the groups. Or you can have a curvilinear interaction, where now you've got an interaction not between just gender and hours, but gender and the hour squared term. And now you can have the shape of the curve changes. So this got me my first job. It was a curvilinear interaction, kind of waving my hands in front of a department, kind of going over the results. So what we saw was, like, if you're a kid who lives in a safe community, a safe environment, parental control means almost very little. On average, you have low levels of behavior problems. It didn't matter if your parents were really out to lunch or your parents were really on top of you all the time. Kids tended to, you hung out with good friends, you tended to be fine. You live in a more high-risk environment where there's gangs and crack houses and stuff. It's like as the environmental risk increased, the you became stronger and stronger. It actually shifted a little bit too, to the higher level of control. So that now you do too little control, the kid's got problems. Too much control, the kid's got problems. Interestingly enough, if you hit it just right, it was the same level of behavior as the kid in the good neighborhood with the good friends. But you have to get it just right. It's demanding. It's tough being a parent in some communities. You live in a safe suburban, rural, whatever, or safe suburban neighborhood, it's easier to be a parent because you can screw up one way or the other and the effect on the kid was much less. Those higher risk communities, it's much harder to be a good parent because you screw up one way or the other, the consequences on the kids were a lot worse. So that's a curvilinear interaction. You can finally, and I think this is the last one, you can have even cubic. We've done the quadratic where it's squared. You can do cubic terms where you add it's not just squared, but now you multiply hours times hours times hours. And you can keep adding little twists in the curve. And that's one way of seeing that plateau. You can kind of see that might be a way of detecting the plateau because notice it doesn't go flat, but it's a way of kind of kicking back up at the end to flatten out a little bit. But very hard to detect because it's controlling for even more variance. So now you're looking at smaller R-squared changes often, and you need bigger and bigger samples. So again, that wraps this up. I'm sorry to keep you a couple more minutes, but the idea with that is just to hammer home one more time before we wrap up this material, the notion of the model, the regression equation you pick will fundamentally shape the results you get. If you say, I think it's this, you put in a model that says 2 parallel lines, it will give you the best result for 2 parallel lines. It doesn't matter if they're curved. It'll still do whatever you tell it. Thanks. See you next week.